When you make a video call across the ocean or stream a movie to your phone, the process feels completely detached from the physical world. You press play, and you likely picture your data beaming up into the sky, bouncing off satellites and dropping instantly back down to your device. The reality is firmly anchored to the ocean floor. Almost all of our international data actually travels through a sprawling, physical network of fiber optic cables resting at the bottom of the sea. This animated diagram shows exactly why we rely on the ocean rather than space. If you calculate the total bandwidth capacity of the entire global satellite network, it amounts to this tiny sliver on the left. On the right is the data volume of just one single subsea line, the Maria cable. Satellites simply lack the physical capacity to handle the sheer volume of global traffic. The concept of a wireless cloud is an illusion. Our digital world depends on the survival of delicate glass threads stretched across some of the most geographically extreme environments on the planet. Before dropping thousands of miles of cable, engineers analyze this rugged ocean floor to avoid active fault lines. Surface ships deploy multi-beam sonar, sending acoustic pulses to the seabed to measure returning echoes. This precise map locks in a flat, safe route. Once the path is set, the loading phase begins. Thousands of miles of fiber optic cable are fed into specialized ships, coiling tightly around giant internal turntables designed to manage the line's weight and tension. Laying thousands of miles of cable is a logistical operation where the ship's course is dictated entirely by the contours of the seabed. The highest physical risk to that cable occurs right off the coast, in the shallow waters of the continental shelf. Commercial ship anchors and heavy fishing nets drag along the seabed here, making an exposed line an easy target to snag and snap. Protecting the connection requires heavy industrial machinery. Crews deploy a mechanical steel plow weighing up to 30 tons, lowering it directly onto the ocean floor. The ship tows the structure like a tractor in a field. A heavy blade carves a trench into the seabed, while a built-in guide instantly feeds the heavily armored cable into the fresh groove before the sand can collapse back in. This top-down schematic highlights a major logistical problem. Eventually, your new route will intersect with an older live fiber optic line. You cannot drag a 30-ton steel blade over existing infrastructure. To cross safely, the ship stops and winches the plow off the seabed. They lay the new cable gently over the old one, leaving a 1-kilometer section completely exposed. To secure this gap, they send down an ROV, a remotely operated vehicle. Using high-pressure water jets, the ROV blasts the surrounding sand away, allowing that final exposed segment to sink safely into the seabed. In these busy, shallow zones, preserving global connectivity means using heavy marine machinery to proactively bury and hide the infrastructure from human hazards. As the ship sails further offshore, the environment shifts. The continental shelf drops away, and the water depth rapidly plunges past 1,500 meters. At these extreme depths, anchors and fishing trawlers cannot reach the seabed. With external human threats removed, the physical requirements of the cable change. This split-screen illustration compares the two designs. On the left is the thick, steel-armored cable necessary for shallow waters. On the right is the deep-sea design. Without needing heavy external protection, the cable is reduced to the thickness of a standard garden hose. The time-consuming plowing process stops here. For thousands of miles across the deep ocean, the ship acts as a moving spool, carefully managing the tension of the lightweight cable to ensure it sinks evenly to the dark seabed below. Out in the deep ocean basin, engineers trade active defense for passive endurance, letting gravity and sheer isolation protect the network. Despite this careful planning, the ocean is a violent environment. Subsea cables are severely damaged or severed completely 2 to 4 times a week somewhere around the globe. Keeping data flowing requires an endless cycle of physical maintenance. When a fault occurs, specialized repair ships are dispatched to the exact coordinates. They send equipment to the seabed to cut the damaged section entirely, and then slowly hoist both functioning ends of the line miles up through the water column and onto the ship's deck. Technicians then begin a microscopic, days-long procedure known as splicing. They meticulously align the hair-thin glass fibers of a new spare cable with the old ends, physically fusing them together to restore the data signal. This creates a precarious physical situation. You have a massive steel vessel floating in open water, tethered to a fragile strand of glass that drops miles down to the seafloor. If the ship drifts even a few meters off its position, the tension will immediately snap the glass. To solve this, the repair ship relies on a dynamic positioning, or DP, system. This 3D wireframe diagram illustrates how the DP computer constantly processes external forces. It pulls in real-time GPS data, measures wind speed, and calculates ocean currents, feeding all those overlapping variables into a central predictive algorithm. Based on that algorithm, the system sends continuous commands to the ship's azimuth thrusters, specialized propellers beneath the hull that can rotate 360 degrees. By making microscopic automatic adjustments to the angle and thrust, the ship mathematically cancels out the external vectors, holding its exact center coordinate down to a single meter. Preventing global internet blackouts comes down to a continuous physics calculation, using thrusters to precisely cancel out wind and tide, so that the glass thread never reaches its breaking point. The physical internet is built on the convergence of specialized mapping, 30-ton plows, and algorithm-driven positioning. Every time you load a website or stream a video, your device relies on this hidden, physical lifeline. Our digital lives continue uninterrupted because specialized mariners are out there right now, actively battling the ocean to keep the continents connected.